Good day, everyone, and once again we're back together. All right, so today I'll be looking at the IEB exam from 2023. Of course, I know that some of you are preparing for those exams, right? So if you haven't subscribed, please do the right thing. Otherwise, I hope that you'll enjoy the rest of this paper as I discuss it with you. Let's start. Okay, right, so we start with the multiple choice section. Right, I'm going to start with the very first one. They say to us the unit for power is the watt. This may also be written as follows. Right, now please remember, watt, that's power, is the rate at which work is done. Okay, but if you think about it, when we take work done, it can be change in kinetic energy. So you can say half mv squared, right, change in half mv squared, divided by time, which obviously is measured in seconds. So mass would be measured in kilograms, right? Velocity would be meters per second, but remember this is all squared, divided by time, which is in seconds. So what you end up with is kilograms, meter squared, per second squared, right, divided by seconds, which is, in this case, you can say another per second. And so you end up with kilograms meter squared per second cubed, right? Okay, another way that you could have looked at this is sometimes power, we can write it as force multiplied by velocity, the average velocity, right? And our force is mass times acceleration times the average velocity, which this is in kilograms, acceleration is in meters per second squared, but velocity is in meters per second, right? And again, it gives us exactly the same, meters squared, right? So those bases are the same, per second cubed. So the correct answer there should be C. Okay, right, let's go on to the next one. They say a ball is dropped from a height h and hits the ground with a velocity v, right? They say the speed of the ball at the moment when it reaches half its initial height. Okay, so if you think about it, so suppose here we are, we've got a ball, we're dropping it, we know its initial velocity is 0, right? We want to find the final velocity, right? So if we use the equations of motion, right, remember, in this case, we've got height, right? What we're not given there is time, isn't it? So I can say, look, v squared is equal to I squared, or vf squared, plus 2 times a times delta x, right? Or delta y in this case, because it's falling, right? So initial velocity is 0, plus 2 times our acceleration, okay? Times delta y is our height. So to get VF, right, that would be the square root of 2 times A, or you can say G, times H, right? Now, to get to half its height, let's find out what the velocity would be if we get to half the height. So the velocity, right, if I use that formula there, that would be square root of 2, okay, and by the way, this is V, right? That would be square root of 2 times A. Now it's 1 over 2H, right? So that means that I can take that 2 times a half, that will give me 1, so I end up with square root of AH. Now, if I were to compare this when I'm at half the height, right, to that when I'm at full height, do you see that we've got a square root 2 missing there, right? So which means that this VF would be the same as that divided by square root 2. So this would be V divided by square root 2. So which means in this case our answer is this guy over here. Okay. Right, you could have also used energy principles for this answer, okay, to find that out. Okay, now let's go to the next question. They say a heavy ball of mass 6m is traveling along a straight horizontal surface at a speed of v, right? It collides with the stationary light ball of mass m. The surface on which they collide is frictionless, right? The heavy ball continues at half its original speed after the collision. The speed of the ball, the speed of the ball, of the light ball rather, after the collision will be equal to, now in this case, let's try and do this together, right? We've got a heavy ball, okay, and we've got a light ball. We know this guy must have been stationary at the beginning. They told us this guy is 6m and moving at a speed of v. But afterwards, we know that the speed, okay, this guy will be moving at half its velocity, right? At 6m. So we want to know what will be the speed of the light ball, right? So if I say momentum before is equal to momentum after, right? So the sum of their momentas, this will be mass 6m, right, times the velocity, which is v, is equal to, on this side I've got 6m times half v, right, plus m times vf. So I'm looking for this final velocity, right? This gives me 3mv. This is 6mv. If I take this to the other side, it becomes 6mv minus 3mv will give me 3mv, right? That's mvf. And if I divide both sides by m, notice this cancels with that with that, and I'm left with vf is equal to 3v. Right, so that is what I will get in terms of my velocity, right? Okay, so that's what I get there. Right, now they say to us a person weighs 750 newtons. The person stands on a scale placed on a floor of a lift. The lift travels up and down in a tall building. They say which row in the table describes the motion of the lift at the moment when the scale reads 700 newtons, right? So I want you to note in this case that the scale reads less than what the person weighs, right? Now, I want you to remember, inside of a lift, what will happen is that the scale, unless the lift is stationary or the lift is moving at constant speed, right? In which case, the scale will read exactly what the person weighs, right? But suppose the lift is moving up and it's accelerating. What the lift will read is the force that is applied upwards, okay? So in that case, it would mean the force up would be the one that is greater, right? If it's accelerating. But if it has to read less, right? If the lift was going down, it would definitely read less. But let's see the options that are given, right? If we are moving up and we are slowing down, now think about it. If we're slowing down, even though we're moving up, it means the force downwards is the one that is greater than the forces going upwards, okay? And remember what I said to you, that the lift is actually reading the value of the force that is applied upwards, okay? So I would believe A, right? And moving at constant speed, definitely not. Okay, moving downwards and slowing down, that would mean that the force downwards is much greater. And that force, I mean, it would be a much bigger force in that case, going down. All right, so in fact, no. The upward force would be bigger because remember, it's slowing down, right? So definitely the correct one would be A, okay? Because it tells us that the force that is applied is smaller than the force that is going down, right? So, all right, I hope that makes sense. Right, the next one says the diagram below shows a trolley held at rest at the top of a frictionless slope, right? They say what information is required to calculate the speed reached by the trolley at point X. Now, I want you to note in this case, first of all, they told us that this guy is held at rest. So the initial velocity should be 0, right? Now, what's going to happen? Because it's a frictionless surface and there's no applied force, it means mechanical energy will be conserved, right? So to get the velocity here, all we simply need are the differences in the height, okay? Because that is what will determine the velocity there, right? Remember, when you're using mechanical energy principles, velocity can actually, mass rather, mass can actually cancel each other. So we don't necessarily need the mass, right? So I would go with B and say it is definitely the difference in that height. H1, right? The length of the slope, not, and all of the above, not really. Okay, right, now let's go to the next one. They say to us we've got an athlete that runs up a flight of stairs at a constant velocity v, gaining a certain vertical height from start to finish. Right, they say the mass m of the athlete can be treated as a point mass, okay, which helps us, right? It took time t to complete the climb, okay? Now, I want you guys to please note, they say the average power output of the athlete is. So, we know that power is the rate at which work is done, right? So, in this case, I can say power is the rate at which work is done, right? But what is work done? That's force, okay, multiplied in this case by the displacement, right? Divided by a change in time. So, what would be my force in that case? Remember, it is work done to, it's work done rather to gain vertical height. So I can actually say this is mgh actually, right? So that's mgh. I've gained height. Remember, the velocity stays constant. That's what they say. So I don't gain any, any kinetic energy in this case. So mgh, right? But how would I get that height? That height, if you think about it, that height would be the velocity, okay, if we use equations of motion, delta x is vi delta t plus 1 over 2a delta t squared. But we know acceleration is 0 because constant velocity, right? But this is our height. Our velocity in this case, right, would be that guy over there, right? Here's our velocity multiplied by the time, okay? So that means that height is velocity multiplied by time, right? So now, if I go and substitute this there and say, look, I've got mg, instead of height, I'm going to put v times delta t divided by delta t. Of course, those can cancel. I'm left with mgv. So that would be how we'd get that power. All right. Yeah, these questions are really not the easiest, but I hope you get the gist of it nonetheless. Right, now they say to us, a bag of clothes pegs with a mass of m, right? So the mass of this guy is m, right? Hangs on a washing line. This causes the line to sag so that the washing line is at an angle, theta, with the horizontal. Now, I want you to please consider this. Okay, so now, which means that you've got this tension over here by the string, but you also have this tension over this side by the string, right? But in this case, I want you to note you've got a vertical component of that tension, okay? But you also have another vertical component from that. So let's say that's T and that's T, right? So now what I want us to quickly do is to notice that the two vertical components acting together will actually be equal, okay, to the weight of this guy, which is mg, right? But now how do I get the vertical component? It's on the opposite side of the angle, right? And in this case, our tension is T, right? So to get that vertical component, let's call it Ty, okay? It would be T, the sine, so this would be T sine of angle theta, right? But you also have the same thing this side, that's T sine of theta, right? So which means 2 times T sine theta, because you've got 2 of them there, right, is equal to mg, right? So to get the value of T in this case, I'll divide by 2 sine of theta. And what I do on the left, I do on the right. Okay, that cancels that with that. So the tension T should be equal to mg divided by 2 the sine of theta. And I think the one that is correct, that would be B. Okay, I hope that makes sense again. Right, now the next one, they say to us a battery with an EMF, right, is connected, EMF E is connected across the resistor R, right, as shown. An ammeter is connected in series with the resistor, and a voltmeter is connected across the battery, right? So they say to us, as the temperature rather of the battery increases, right, the internal resistance increases. Now, remember that EMF is equals to I into R plus small r, or we can say it's equal to V external plus V internal, right? Now I'm going to take you through something just now. They say to us R internal increases. So remember, when R internal increases, right, or rather R internal increases, what it does is that it will increase the value of the internal voltage, okay? So what happens? Our EMF stays constant, so V external will definitely have to decrease, right? If EMF has to remain constant. So definitely we are looking at a decreasing external voltage, which is V, right? So it's between those two answers, right? But now they're asking us about the reading of the ammeter. So the total resistance increases, so definitely our current has to decrease. So both V external and current will decrease. So the correct answer there should definitely be D. All right, now the next one. They say to us a magnet is dropped through a vertical coil, right? What will be the output of the voltmeter connected to the coil look like? Now, under ideal circumstances, you would be taking this magnet through, right? And usually we do that at constant velocity, okay? If that were the case, we know that in this case there would be an induced current, right? So at constant velocity would definitely follow this trajectory, right? But now we are dropping it, okay? So what's going to happen? It's going to keep moving faster and faster, and the faster the magnet moves, the greater the induced the induced current, right? So in this case, I will start with a smaller value for current, okay, or for voltage, right? And it will increase as it goes. So I think the only one that shows that, right, a smaller value, then a bigger value, right? So in this case, definitely it would be C. I hope that makes sense, because we're dealing with a velocity that is not constant. Okay, right. And finally, they say to us, high energy light is shone onto a copper plate. Electrons are emitted from the metal plate, all right, from the copper plate. Which combination will be true when the wavelength is decreased? Now, please remember, the energy of a photon, it's Planck's constant multiplied by the frequency. But we can write it this way, hc over lambda. So they are saying to us, we are decreasing the wavelength, right? So the smaller the wavelength, what happens to the energy of the photon, right? It will increase the energy of the photon, right? Which will increase the kinetic energy, because remember, EK is definitely going to be equal to the energy of the photon minus the work function. This guy stays constant, okay? Constant, you get the point, right? So if I increase the energy of the photon, it will definitely increase the kinetic energy, right? Okay, so it's between these two. Now they say the number of emitted electrons. Now remember that what increases the number of emitted electrons will be increasing the intensity of the light. So in this case, we didn't do anything to the intensity, so that has to stay the same. So in this case, our answer is D. And I hope that makes sense, ladies and gents. I hope that you'll be able to understand this, and we will be back again with question 2. And now we start with question 2, all right? So they say to us, we've got a ball which is initially thrown vertically upwards at 2.8 meters per second from a distance of 0.9 meters above the ground. It bounces on the ground. The motion of the ball is represented on the velocity time graph below. Ignore the effects of a resistance. The graph is not drawn to scale. Now, if we look at this graph, first of all, this tells us that we start with an initial velocity of 2.8. Okay, so there it is there. Okay, and in this case, as the ball goes up, what happens? The velocity decreases until we reach that maximum height at T1, right? And at T1, okay, we stop momentarily, right, at maximum height, and then we start going down, okay, up until we reach the ground. This would be the velocity when we are now on the ground and we bounce off the ground. So remember, once it gets to the ground, okay, then it will just stop momentarily and then change direction. So this is when it is now leaving the ground. So this is when it is now bouncing off the ground, okay? And of course, it does the same thing, gets to maximum height, another maximum height, okay, right? And it comes back down, okay, another bounce in this case, changes direction, and gets to maximum height. So that's what the motion of that ball looks like, right? We know it leaves the ground at 2.8. Now they say to us, why are the bold lines on the graph parallel to one another? Now remember, what do these actually represent? They represent, in this case, the motion of the ball when it is moving under free fall, right? When it is in free fall. This is when gravity is the only force that's acting on this ball, right? So in this case, why are they parallel? Because in this case, they represent gravity. So remember, the gradient of the graph represents gravity. So they represent gravitational acceleration. Okay, So they represent gravitational acceleration. Okay. We can say this is when the ball is in free fall, and as a result, it is moving at 9.8 meters per second squared. Now they say to us on the axis provided, sketch a position versus time graph for the entire motion of the ball, right? Okay, represented on the velocity versus time graph. No values are necessary. So the position time graph would kind of take on that kind of a scenario, right? Because what happens? We're going to start at 0.9 meters above the ground. Remember, that's when they said the ball started, right? And then what happens? We go on to maximum height, okay? And I said we reach that maximum height, then we come back to the ground, okay? Momentarily, there's that pause, and we get to maximum height again, right? In fact, let's not make it the same. Say a second maximum height, okay? And we come back to the ground, and in this case, again, another, and we now reach another maximum height. Let's make it even smaller, okay? Right, the third maximum height. So this is what your position versus time graph would look like. As I said, it will take on the shape of what I have drawn there, showing us the position of the ball at every single time. Now, just so that we, know exactly, show that we know exactly what we're talking about. So this would be time t1. This is when we reach maximum height, isn't it? Okay. And in this case, I don't think there'll be anything else that we know of, right? They've already labeled our axes. Okay. Right. Now let's go on to the next question. They say on the graph you sketched in 2.2, label T1, that is shown on the velocity time graph. Well, we've already taken the liberty to do that. Okay. So I think that's 2 marks for free for us there. Right, now they say to us, calculate T1. Okay, now there are 2 ways in which I'll show you how to do that. So remember, what do we know? We know that our initial velocity was 2.8 rather. We know that it gets to a velocity of 0 at T1, right? So I can say, look, let's take, in this case, equations of motion and say, well, we know Vf is equal to Vi plus A delta T. Right, now I'm going to assume upwards motion is positive, right? So my final velocity, this is when it gets to the maximum height. My initial velocity is 2.8, okay? Right, plus, remember acceleration is 9.8, but remember it is downwards, right? So that would be minus 9.8 delta T. So that will be minus 2.8. If I take this to the other side, is minus 9.8 delta T. And if I divide by negative 9.8, okay, so what do I get? Right, so I'm going to say 2.8 divided by 9.8. Of course, those negatives will cancel each other, right? So this will give us 0.29, shall we say? Right, so that will be 2.9 seconds, right? Now, another way that you could have done this is to use the gradient of the graph. So please remember that the gradient underneath this graph gives us acceleration, isn't it? So we know the gradient, right? So that's change in V divided by change in T. So we know the gradient would be negative. You can tell that's a negative gradient there. So that's going to be, right, so you can choose that one. So here you've got T1 and 0. Okay, here you've got 0 and 2.8. Okay, so I'm going to say y2 minus y1, so that's 2.8 minus 0 divided by 0 minus t1. And of course you can do your mathematical gymnastics there, and you'll see that t1 gives us exactly the same answer of 0.29 seconds. All right, please take the liberty to do that for yourself, okay, and you'll see that you get the same answer. All right, so now they say to us, calculate the velocity v1 with which the ball hits the ground on its first bounce, right? So now, what do we know? We know that when the ball left, now please, I want you to listen very carefully, right? So this is when it reaches the ground for the first time, right? Let's say this is position A, B, this is when it comes back to the same height, and this is position D, right? So remember, this is when it took, this is time t1, right? But what else do we know? We know in this case, from A till D, that the height there is 0.9 meters, okay? And please remember that we've taken up as positive, so that means we're displaced downwards by 0.9 meters, right? Okay, so I'm going to say, right, my initial velocity is 2.8. My final velocity is unknown, that's what I'm looking for. But gravitational acceleration is negative 9.8, right? And in this case, the time taken is unknown. Remember, we can't say 0.29 because we're talking about, in this case, when it lands on the ground, right? So the displacement in that case would be negative 0.9 meters. Why? Because it's displaced downwards, right? So now what I'm going to do is I'm going to use the only equation without time, vf squared. That's vi squared plus 2 times a delta y, right? My final velocity is what I'm looking for. My initial velocity is 2.8 squared plus 2 times negative 9.8 times negative 0.9. Okay, right, and so to get that velocity, we'll just simply take the square root of all of that. Okay, right, so let's try and find that there. Okay, so we've got the square root of, that's 2.8 squared, right, plus 2 times negative 9.8 times negative 0.9, okay, and I get a velocity there. Now remember, we've taken the square root, right? A velocity of 5.05 meters per second. And notice it is downwards, so that velocity ideally should be negative. Remember, when you take the square root, you always say plus or minus. So it's important for us to have that sign. So what is it telling us? It's telling us that the velocity when it gets to the ground is 5.05 meters per second. But please remember, this is downwards. Okay, right, now they say to us on the next one, calculate the time from when the ball is thrown to when it first hits the ground. So the time associated with this guy here, right? Now, several ways in which you can do that. I'll take information from A to D from my sketch, right? From when it left the ground up until, left the thrower's hand up until it reaches the ground, right? I know my initial velocity, 2.8, right? So essentially, I'm looking for the time associated with that. Let me not reinvent the wheel. Okay, so I'm going to say Vf is Vi plus A delta t. My final velocity, I got that to be negative 5.05. Please, it would be very crucial for you to put that negative there, right? So this is initial, which is 2.8, okay? And my acceleration, which is minus 9.8 delta t. Okay, so if I take this to the other side, I get minus 7.85, negative 9.8 delta t. And here's another very important thing, ladies and gents. If you ever get a negative time, then that's an indication that something went wrong in your, either in your substitution or in your calculation, right? So I get my time there to be equal to, so 7.85 divided by 9.8. I'm not going to put in the negatives there because, they cancel each other, right? So this gives us 0.8 seconds. Now, what you could have also done is you could have found the time from when it left from its maximum height, okay? So you could have used initial velocity being 0 from the maximum height up until it gets to the ground, okay? Now remember, the velocity minus 5.05, the initial velocity there, okay? Now, what this would do is you'd be able to calculate the time taken from there, but remember you also have the time for when it reaches maximum height. Where did you calculate that time? Plus 0.29. So what you would do is say, all right, my initial velocity was 0, final velocity 5.05. So I'd say Vf is equals to Vi plus G delta t. Okay, that's negative 5.05. This would be 0 plus negative 9.8 delta t. And what I'll do is divide by negative 9.8 on both sides. Okay. Negative 9.8. So I get that time to be 5.05 divided by 9.8. I get 0.515. Okay, so that time 0.52 seconds. But remember, I still need to add this to the 0.29. Okay, so I add this to the 0.29 and you'll see I get the same time. Okay, of course there'll be a slight difference there. It says 0.81 seconds, but I mean it's exactly the same thing, right? Okay, so that is how the cookie crumbles. I hope that is understood. Remember, this is the time it took from when it left up until it gets to that maximum height. So it's the 0.29 and then we added it to the time till it gets to the ground, okay, which is the 0.52, and that's how we got the 0.8 seconds. All right, ladies and gents, I hope that that makes sense. All right, we will move on to question 3. Right, and now we move on to question 3. All right, so they say to us, we've got a group of students that investigate the motion of a trolley. The trolley starts from rest, okay, very important, okay, and is accelerated in a straight line along a frictionless horizontal surface, right? They say the students measure the change in position of the trolley during various time intervals. Right, now they say to us, state the independent variable for this investigation. Right, now I want you to think about it. When you look at this table that is given to us, okay, the independent variable there is time, right? The the time taken, right, for the trolley to complete each position or change in position. So definitely it is the time taken. Okay. Right. Now they say to us the change in position of the trolley measured during each time interval is shown in the in the table below, right? So we've got that table, okay? And they say in the block below, write down the value of t squared. Now note, you've got time here, and they give you the square of time. Okay, they say t squared, that is missing from the table. Round off your answer to 1 decimal place. All right, so t is 1.7. So that's 1.7 squared, and that gives us 2.89. So that's the value, but they said to 1 decimal place, so this will be 2.9 seconds, right? Actually seconds squared, but in this case they just said the value. So that's 2.9. Now they say to us, plot a change in position versus time squared graph, right, on the x-axis on the graph paper provided on the next page. Okay, so we now need to take all of these values and we need to plot them. Now remember, when you're using graph paper, right, you must use at least half of your axes, right? It should be actually more than your axes, right? Half your axes, that is. So if I look at the time squared axes, they start from 0.3 all the way to 9. That's our x-axis, right? So can I say, let's say if we said 1, 2, 3, 4, 5, 6, 7, 8, 9, definitely it would be more than half of it. So that's exactly what I'm going to do. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So that would be my time squared axis. So this would be t squared, which is second squared, right? And then for my y-axis, which is my delta x, it moves from 0.2 to 3.6. So let's see a scale that we can choose. If we said this is 1, 2, 3, 4, yeah, it would definitely be more than half, right? So definitely I'm going to go with that. So this is change in position, and this is in meters. Now, ladies and gents, it's very important when you do these type of graphs that you plot the the axes as accurately as possible. I'm gonna do 2, and after that I'm just going to skip so that you just get the gist of it. Okay, so the first 2 values that we've got 0.3 and 0.2 respectively, right? So my time squared values increase in terms of 0.2, right? How do I know that? The difference between these divided by the number of cells that you've got 5, right? So that which means it's 1 divided by 1 divided by 5, which is 0.2, right? So the first one, we've got 0.3, which is somewhere over there, right? And on the y, we've got 0.2. Okay, so we've got 0.3 and 0.2. So on my y, I'm increasing by 0.1 per cell, right? So in this case, that's why we've got that as 0.2 over there, right? Okay, the next value that we've got, I've got them right here in front of me. So it's 1 and 0.4. So that's 1, okay, and 0.4. So that's 1, 2, 3, 4. So this would be the value over here. Okay, right, you can skip and get to the end of this, but it's quite a tedious process. And then it was that missing value, which was 2.9 as well as 1.2. So 2.9 and 1.2. So that's the value there. Okay, and we've got 4 and 1.6. So we've got 4 and 1.6. There it is over there. And we've got 6.8 and 2.8. So that's 6.8, which is here, and 2.8. Right, so there it is over there. Okay, and we've got finally 9 and 3.6. So we've got 9 and 3.6. So there's 3.6 over there. Right, so now what we're going to do is use our ruler. Okay, and let's see if our... Okay, so what we are going to have to do here is that we're going to have to take a line of best fit. Now, you do agree with me that this is the best I can do. Okay, which one would have most of my points in it? Yeah, I think this would be the line, isn't it? That has most of the points in them, right? So I would take definitely this line here. Okay, right, so that's our graph. And then now they say to us, calculate the gradient of the graph that you have plotted, include units in your answer. Okay, now please remember, when you calculate the gradient, take the points that would have been included, right? So what I'm going to do is I'm going to take that point as 6.8, which is this point over here. And I'm also going to take the one where we've got 4. So that's the 6.8 and 4 value. Okay. Right, so I'm going to say my gradient. Okay, M. That's going to be change in X. Okay, change in Y divided by change in X. But remember, change in Y is delta X, right? Over change in time squared. So that's change in X divided by change in time squared. So my change, I said I would take these two values. That's going to be 2.8 minus 1.6 divided by, now please remember they said we take the SI units as well, so that would be meters, divided by, okay, 6.8 minus 4. When the time squared was when it was 2.8, when displacement was 2.8, time squared was 6.8, and when it was 1.6, my time squared was 4.0. Okay. Right. Am I correct there? At 2.8. Okay, right. So let's say, okay, let's calculate there. We're going to have 2.8 minus 1.6, right, divided by 6.8 minus 4. Okay. Right, I get a value of 0.43. And remember, this is second squared. So this would be meters per second squared, right? So the gradient would be 0.43 meters per second squared. I hope that makes sense, ladies and gents. Right, now they say to us, use the equation of motion, use an equation of motion and the gradient that you calculated in 3.4 to determine the acceleration of the trolley, right? Now, I want you guys to please note, right? I found out from this that actually, right, this guy gives me an acceleration of 0.4, right? Now they're asking us to use equations of motion. So what we can do is take the change in position, right, against the change in time, right? And in this case, we can actually work out the velocity at each time interval, right? So we can say, look, I can take the velocity, right? Okay, that's going to be change in position divided by change in time. Okay, so at any given interval, so let's just pick the very same one that we used, right? So this is going to be 6.8. Okay, remember I'm taking against time, right? Divided by time. So in this case, I'm going to say change in position was 2.8 when the change in time was 2.6. Okay, so I'm going to say this is 2.8 divided by 2.6. Okay, what's that velocity there? Okay, I get a velocity of 1.0. Okay, let's say 1.08 meters per second. Okay, and velocity 2. Okay, let's take another value, right? I took this one here at first. I'm going to take another, this one, 1.6. My change in position was 1.6 when my time was 2.0, okay? So I'm going to do exactly the same thing. Okay, I've gone too far. So that's 1.6 divided by 2.0, right? And what does that give us? Right, 3 point, I said that's divided by 2. So that's 0.8 meters per second, right? Now, I want you guys to please note in this case, I've got differences in the change in velocity, right? So I'm going to say, to calculate acceleration, that's change in velocity divided by the change in time. So I'm going to take that, that's 1.08 minus 0.8 divided by, now remember the time there, I'm going to take the difference in time over these two. So 2.6 and 2 respectively. So that's 2.6 minus 2. Okay, so let's calculate. So I've got 1.08 minus 0.8, okay, divided by 2.6 minus 2. Okay, I get 0.47. Okay, so 0.47 meters per second squared. And you can see, ladies and gents, how those are very close to each other, right? In terms of the one that we calculated versus the one that we actually derived from the graph. Okay, right. So we could have used equations of motion as well: initial velocity, final velocity against time, right? And in that case, that would have given us the velocity, the acceleration. Okay. Right, and in this case, they say use your graph to determine how long it will take the trolley to travel a distance of 3 meters. So now to interpret that from the graph, okay, so I'm going to take my ruler again and say when my distance is 3 meters, there it is over there, okay, I want the corresponding time value. All right, so what time would that correspond with? So there it is there. Okay, so that would be 7 looks like 7.4, right? But remember that's time squared is 7.4 seconds squared. So to get time, that would be the square root of that. Okay, and in this case, what we are simply going to do is say what is the square root of 7.4, and we get 2.72. Okay, and remember this is in seconds, right? I hope that was really helpful, ladies and gents. Okay, that is how I would have answered that question. Right, as we are going to look at question 4 next. Right, so now we move on to question number 4. They say a bus is accelerated uniformly forward along a level road. A book lying on the floor experiences negligible friction. Okay, so first of all, we've got a book that is on the floor, right, that has negligible friction. And they say to us, while the bus accelerates, right? And they say to us, an identical book lying in the middle of a flat seat, right? So there's another book that's on a flat seat. In the bus experiences significant frictional force, right? And remains at rest, okay? Right, on the seat as the bus accelerates, right? And it would make sense why it would remain at rest, because in this case, because of the amount of friction that is there, right? Now, they say to us, define frictional force. Remember that friction is the force that opposes motion, the motion of an object, right? Okay, so frictional force is a force that opposes the motion of an object. Now, they say to us, is there a resultant force acting on the book that is on the floor, right, as the bus accelerates? Okay, so remember, because there is no frictional force, okay, so there is no net force in this case. So F net will be equal to 0, or we can simply say that there is no net force acting on the book, acting on the book rather. All right, there's no net force acting on the book because there is no frictional force, because there is no friction. Okay. All right, so right, now they say to us, draw a labeled free body diagram showing the forces that act on the book resting on the seat. Now remember, the one that is on the seat does experience friction, right? They say as the bus accelerates forward. Now they say forward is to the right of your page, right? Now I want you to note, if we're moving in that direction, remember, as the bus accelerates that way, what happens? It means that the book wants to move in that direction, but in this case, because of friction, friction would want to oppose the motion. So this is the motion of the bus, right? And so it would cause the motion of the book. Now, because there's friction, remember, the one that is on the floor that has negligible friction, right, would actually, as the bus accelerates to the right, that book would go to the left, right? I want you to think about it, okay? So it would actually go to the left as the bus accelerates. But this one, because there's frictional force, right, as it wants to go to the left, friction opposes it, and so friction would be in that direction. So frictional force, okay, so frictional force in that direction, and you would have the normal force And please try to indicate in your diagram, right, so that we can see which force is bigger than which. Okay, so the length of your lines should kind of indicate to us which force is greater, right? So this would be the gravitational force, or we can just simply say the weight of the object. Okay, right, now let's go on to the next question. They say to us, describe the motion of the book on the floor as observed by a passenger that is on the bus, right, while the bus is accelerating forward. Now, as I said to you, so the one that is on the floor, as the bus moves forward towards the right, the book would actually move to the left. Okay, so the book would move to the left, would move to the left. Okay, or you can say backwards. All right, we can say backwards relative to the position. Okay, relative to, so that's relative to the passenger. Okay, right, I hope that makes sense, ladies and gents. Okay, right, now let's go on to the next question. They say to us, the mass of each book is 0.1 kilograms. The coefficient of static friction, right, on the book is 0.4, right, that is on the seat. Okay, they say calculate the magnitude of the frictional force that must be overcome for the book to slide. Now remember, we say that friction, okay, so in this case we're talking about static friction, right, is equal to the coefficient of friction multiplied by the normal force. But what I want you to appreciate, ladies and gents, is that if that's our normal force, remember, in this case, it is opposing the weight of the book. Okay, so we can definitely find out what the weight is. That's m times g. That's 0.1 times 9.8. Okay, so that's 0.98, right? And so the coefficient is 0.4 rather, multiplied by the coefficient, or rather the normal force, okay, which is equal to gravitational force. That's 0.98. And so what do we get for that? We say 0.4 multiplied by 0.98, and you will get 0.4, right? So our static frictional force, okay, would be 0.4. Okay, right, newtons. And then in this case, they said calculate the magnitude of the minimum forward acceleration of the bus that would cause the book on the seat to slide, right? Now, I want you guys to note, so we want the acceleration that would cause the book on the seat to slide. So in order for the book to slide, it would need to overcome the static frictional force, right? So that means in this case, right, I want you to note, okay, so F net is equal to MA, right? And in this case, we want the minimum forward acceleration, right? So that minimum acceleration must actually, in this case, overcome just then the static frictional force. So I would say the net force must at least be, right, the value of the static friction. So that would be 0.4, okay? And the mass of the book in this case is 0.1, okay, multiplied by the acceleration. So I'll divide both sides by 0.1. So our acceleration must be 4 meters per second squared. That is the minimum acceleration that the book, or rather the bus, must have. Okay, right, now quickly, they say the bus accelerates with an acceleration greater than the value calculated in 4.6, right? Will the book on the seat slide towards the front of the bus or towards the back of the bus? Briefly explain. Right, now, when the bus accelerates, right? Remember, we said if the bus accelerates in that direction, right? The book would want to move in that direction. Of course, friction would prevent it, but if we overcome friction, the book should move to the back of the bus. Okay, so in this case, it would go to the back of the bus, right? Okay, but why is that? Okay, because in this case, remember that the net force, okay, the net force, now we're not talking about the net force on the bus, we're talking about the net force on the book. Okay, or rather I should say the acceleration will be in the direction of the net force, right? So remember, the acceleration of the book will be in the direction of the net force, according to Newton's second law, right? Okay, right, I hope that makes sense, guys. Right, so we can also state the fact that if you think about the law of inertia, that's Newton's first law, right? If I'm accelerating forward, what happens? Because of inertia, okay, I'd want whatever object would tend to move backwards, right? In this case, but because of Newton's second law, it will actually accelerate backwards. So it will definitely be to the back of the bus because the greater force is towards the back. Okay, right, so that is question number 4. Right, let's move on to question number 5. Right, so question 5 says we've got 2 blocks, which is mass 1 kg, which is A, and B, mass of 5 kgs that are pulled along a horizontal surface by rope 1. They are connected by rope 2. Okay, while they are moving, block A experiences a frictional force. Okay, so this guy would experience friction, okay, of 3.9 newtons, and block B experiences friction of 19.6 newtons, right? Now they say after rope 1 has pulled the system for 0.5 seconds, rope 2 snaps. The velocity of block A is represented against time on the graph below, right, which is not drawn to scale. Right, now, first of all, I want you to notice on this graph, there it is, our acceleration was much smaller, right, when we're pulling both, but at 0.5, do you see that that acceleration starts becoming much higher, right? So it's showing us that actually the acceleration changed because one of the masses was actually detached from the system. Right, now they say to us, define acceleration. Remember, acceleration is the rate of change of velocity. Okay, so that's the rate of change in velocity. Okay, that's what acceleration is. Right, now use the velocity time graph to calculate the acceleration, the magnitude of the acceleration of the system while force of rope 1 is being applied before rope 2 snaps. Now remember, in this case, to get the acceleration, this is a velocity time graph. So we're going to calculate the gradient of the graph, right? So we're going to say acceleration is change in velocity divided by change in time, right? So I'm going to take the values there. So that's 1.2. So this is 1.2, 0.5 and 1.2. And 1.2 there, right? So I'm going to say change in y, 1.2 minus 0, divided by change in x, 0.5 minus 0, right? Change in y divided by change in x, and in this case, that would mean that my acceleration would be 2.4 meters per second squared. Oh, I hope that makes sense, ladies and gents. Okay, sorry about that. Now they say state Newton's second law. Okay, remember, we say that if a resultant force acts on a body, the body will accelerate in the direction of the resultant force. And that acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Otherwise, ladies and gents, you can always state that the net force is equal to the rate of change of a body's momentum. Okay, right, that's another way of saying it in a shorter way, right? They say draw a labeled free body diagram showing the forces acting on block B in the first 0.5 seconds described. The relative sizes of the force must be clear. Okay, very important. Now, when we look at block B, right, it's being pulled by rope 2, right? But it's experiencing friction, but we also have the normal force and the friction. Right, so, okay, I know it's accelerating to the left, so it means the greater force must be the force of rope 2 on rope 2. And we've got the frictional force. Now, relative to the size of rope 2, frictional force must be actually smaller. Okay, we also have the normal force going down, gravitational force, the weight going down, but we also have the normal force going up. And please, those two must be more or less the same size. Okay, so that would be the normal force over there. Right, so now they say to us, calculate the tension in rope 2 before it snapped. Right, now I'm going to say, using that free body diagram, F net is equal to MA, right? But what is our F net? It's going to be the tension of rope 2 minus, we can say plus a negative frictional force, and this is equal to MA. Remember, we're just looking at rope 2, right? So I'm looking for that tension minus the frictional force. They said is 19.6. And this is the mass. What's the mass of rope 2? That's 5 kilograms. And the acceleration. Right, you remember we calculated the acceleration of the entire system. That's 2.4 meters per second squared. So that's 2.4. So let's find out the tension of rope 2. That would be 5 times 2.4, okay, and take the 19.6 to the other side. We can add that there, and so that would be 31.6 newtons. Okay, right, so that would be the tension of our rope. Okay, hope that makes sense. They say determine the magnitude of the force that rope 1 was exerting before the first 0.5 during the first 0.5 seconds of the motion. Now if you think about rope block A, so that would be the force of rope 1, that would be the tension on rope 2, that would be friction, okay, acting on it, I mean the horizontal forces, right? And it would result in the same acceleration. So in this case, what we can say is that again F net is equal to MA, okay, and in this case we're looking at block A, right? So it's going to be the force of rope 1, right, plus negative tension on rope 2 plus the frictional force, negative friction, and this is MA. So the force of rope 1 minus our tension, we got that to be 31.6, minus the frictional force, right? And let's remind ourselves that friction was 3.9. Okay, so that's 3.9 is equals to the mass. Okay, so the mass on the first trolley was 1 kilogram. So that's 1 times 2.4. Remember, the acceleration is still 2.4. And so the force of rope 1, we'll say, well, that's 2.4 plus 3.9 plus 31.6. Okay, so we get 37.9 newtons. Okay, right, I hope that makes sense. Okay, I just looked at the horizontal forces only. Okay, so finally, they say to us, the velocity of block A from the graph on page 12, okay, is shown as a dashed line, right, on the set of axes below. They say on this set of axes, draw the graph to represent the velocity of block B over the same time period. No velocity values are needed. Okay, now I want you to note, of course, what are we going to have for block B, right? You're gonna have this happening up until we get to that 0.5 seconds. But what's going to happen to block B afterwards? It's going to decelerate, right? It's going to decrease in velocity. We don't know how long that is going to take, right? Until it stops. Why? Because of the presence of friction, right? So in this case, we know that we don't know if it's going to stop within that time. They say no values are necessary, but definitely it's going to decrease until it stops. Okay, right, so that tells us what happens on that question. All right, and with that said, question 5 is done. Let's move on to question 6. All right, so let's get into question 6. Right, they say to us a ball is kicked along the ground towards a wall, right? It hits the wall traveling at 4.5 meters per second horizontally. The ball bounces off the wall with a horizontal velocity of 2 meters per second away from the wall. The ball is in contact with the wall for 0.26 seconds. Right, so it's always nicer to just have an illustration. So suppose this is our wall, right? So we know the ball approached the wall with a velocity or a speed of 4.5 meters per second, right? And then we know that it bounced off the wall with a speed of 2 meters per second. Now, please be very careful because we're going to have to, choose a direction here, right? And they did say that the time is 0.2 seconds, 26, the time of contact, right? Now they say to us, define impulse. Now remember that impulse, okay, is simply defined as the product of a force and the period over which that force acts on an object, right? Now they say to us, calculate the change in momentum of the ball, right, as it bounces off the wall, and state the direction of this change in momentum, right? Now notice in this case, let's find out the change in the momentum. So the change in momentum would be the mass of the ball, right? So that's the mass multiplied by the change in velocity. So I'm going to assume that the direction towards the wall is positive, right? So that would be the mass 0.8 times our final velocity. This is after it bounces off the wall. So that would be -2, right? Minus the initial velocity, which is positive 4.5. So it's minus a positive value. So that's minus 4.5. Okay, so what would be our change in momentum? It would be 0.8 rather, into -2 minus 4.5. Okay, man. So that would be -2 minus 4.5. Okay, so we get -5.2. And remember, this is in kilograms meters per second. Right, now note, in this case, we get a negative change in momentum, right? So that means that the change in momentum must be away from the wall, right? So we can say this is away from the wall, okay? Right? Or if you chose a direction, you can say in the direction that you can say to the left or to the right, depending on what you chose as your positive direction. I'll just say away from the wall because that is a consistent reference, right? So they say to us, okay, calculate the magnitude of the average net force experienced by the ball as it bounces off the wall. Right, now I want you to note, in this case, F net, this is the impulse momentum equation, right? It says F net delta T is equal to change in momentum. We just found the change in momentum, isn't it? Right? So we know the time was 0.26, was it? Yes, 0.26. And this is the change in momentum, which is minus 5.2. Right, and we can divide both sides by 0.26. Okay. Alright, I still have that value there. Just divide by 0.26. And I get -20. So, which means our force minus 20 newtons, right? And it we get a negative, but in this case they just set the magnitude, so our force is 20 newtons. Of course, it's showing us that our force is actually away from the wall, which would make sense, right? Right, now in the next question they say, if the time of contact between the ball and the wall was reduced Would the magnitude of the force that the ball experiences be greater than, the same, or less than the magnitude that we have just determined, right? Right, they said write only the appropriate phrase. Now, of course, because I'm explaining here, that's why I'm going to just take you through this. So if I rewrite that formula, it means that the net force is actually the change in momentum divided by time, right? Now, if the time of contact was reduced, this becomes smaller, right? What happens to the force? The force actually becomes much greater, right? And this you would feel, if you were going to catch a ball that's moving at a high speed, right? Usually cricketers would kind of swing as the ball kind of lands on their palms, right? To try and lengthen that time. Okay, so in this case, it means that the force would definitely be greater than. Okay, so you just write that phrase. They said write the appropriate phrase that would be greater than. If they ever asked you to explain, this would be what you would use as your explanation. Okay, right, now the next portion, they say the ball is kicked again, but this time hits a glass door instead of the wall, right? The ball hits the glass door with a horizontal velocity of 5 meters per second and breaks the glass, right? After breaking the glass, the ball rolls a distance of 0.9, okay, before coming to rest. The ball experiences a frictional force of 5.5 newtons as it rolls. Right, now they say state the work energy theorem. Remember, we say that the net work done, right, on an object is equal to the change in kinetic energy. Please, you state this in words. I'm just writing it as a formula so that you see that there's a relationship between the formula as well as the expression, right? The words, the stating of the theorem. Okay, right, now they say calculate the magnitude of the velocity of the ball just after the glass broke. Okay, now what I'd like for us to do, ladies and gents, is that now remember, before the ball hits the glass, they say to us it was moving at 5.5 meters per second, right? And now, right, it experiences frictional force of 5.5 newtons, right? And in this case, the ball moves a distance of 0.9 meters before coming to rest. Okay, now remember that 5.5 meters per second is not the initial velocity, right? This is the velocity before it, broke the glass, right? But immediately after it broke the glass, there must be a velocity. Say this is the shattered glass. So the ball has an immediate velocity after it broke the glass, right? So what I'm going to do is I'm going to say, right, I know that my F net, okay, so frictional force slows this guy down. So F net is equal to MA, right? So I know that my F net is as a result of, so that would be minus F net is equal to the mass of the ball. What was that mass? 0.8 if I remember. Right, so it would be 0.8 times the acceleration, right? And so if I divide that by 0.8, okay, so that's 0.8. Okay, I get 5.5 divided by 0.8. Okay, Right, so acceleration would be negative 6 point, well, we can say 6.9, right? If we are to round that off, meters per second squared. Now, in this case, I can therefore say that actually we could have also used principles of energy. In fact, let's do that because I see they've asked us about work energy theorem. Let's do that instead. So I'll say the net work done on this guy will change the kinetic energy, right? So this would be F net delta X will change the kinetic energy. So I'll say half m Vf squared minus Vi squared. Okay, right. So this would be 5.5 times 0.9, the cos of. Now, please, I want you to note, guys, this would be cos of the angle, right? Remember I say to you, it's the angle between direction of motion and the force in question. Friction opposes motion, so this would be cos of 180. So this would be half of 0.8, right? Our final velocity is 0. Our initial velocity is what we are looking for, right? So I will say, well, let's try and calculate that. That's 5.5 times 0.9, cos of 180, and that would definitely give us a negative value, right? And now on the other side, we've got divide that by half of 0.8, right? So we're going to divide that by 0.5 times 0.8, okay? And we get that minus Vi squared is equal to negative 12.375. Okay, I'll only round off at the end. Of course, the negatives cancel, so the final, I'll say times negative 1. Okay, and so I'll take the square root of our answer, and I get 3.5, right? Remember, we leave it to one decimal place. So the velocity afterwards must have been 3.5 meters per second. And it makes sense. After colliding with the wall, that velocity should be actually less, right? Okay, now they say to us how much energy was transferred, right, from the ball when it broke the glass, right? The time and displacement during the glass breaking can be ignored. So in this case, we can actually compare the energy before. So the change in kinetic energy, that is when it broke the glass. Okay, so in this case, remember, it had a kinetic energy before, so that's half m Vf squared minus Vi squared. Now remember, that's 0.8, right? This is during the process of breaking the glass, right? The ball before was moving at 5 meters per second. And afterwards, it's now moving at 3.5 meters per second, right? So it must have lost some energy there, right? So meaning final, that would be 3.5 squared minus 5 squared, right? And in this case, how much energy did it lose? So that's 0.5 times 0.8 into 3 0.5 squared minus 5 squared. Okay, and we get a change in kinetic energy of negative 5.1 joules. So this is the amount of energy that was transferred from the ball when it broke the glass. All right, so I hope that makes sense. So this is the loss in energy that we made during the process of breaking the glass. Ladies and gents, that was 21 marks, really significant. I hope that made sense. All right, let's go on to the next question. All right, so we look at question 7. They say the planet Mars has a mass of 6.4, exponent 23 kilograms, and a radius of 3,390 kilometers. Right, so if we were going to try and maybe depict what this looks like, so if this was planet Mars, okay, so we know that the radius of Mars would be that 3,390 kilometers, okay, and in this case, the mass of Mars we given there 6.4, 1023, okay, and they say Mars has a small moon. Okay, so let's say there's the moon of Mars, okay, which is at a distance of 20. So in this case, the distance between the two is actually going to be 20.1 times 10 to the exponent 6. Okay, right, I actually should have drawn this a bit better. Maybe let's put the moon there so that we can show the distance much better. Right, so there we go. Above the surface of Mars, right? And they say Deimos is 1.48 times 10 to the power 15 kilograms. Okay, and they want us to calculate they want us to calculate the force, the magnitude of the force that Mars exerts on Deimos, right? So we're going to say, well, force, in this case, Newton's universal law of gravitation attraction, right, divided by r squared. So that's 6.7 times 10 exponent negative 11, okay, multiplied by the mass of Mars, right, that's 6.4 exponent 23, the mass of Deimos, that's 1.48 times 10 exponent 15, all right, now divided by, now please ladies and gents, remember that when we calculate the distance, it's always from center to center. But I see they've decided to take as negligible the center of Deimos, right? So what I'm going to do is I'm going to add the radius of Mars plus the distance that Deimos is away from Mars, right? So this would be the distance 20.1 times 10 exponent 6 plus the radius of Mars. Remember they said it's in kilometers, so we need to to multiply by 1,000 to make it meters. So that's 3,390,000 kilometers. But remember, all of this is squared. So please keep that in mind. Né? Right, so we're going to say, right, so this is 6.7 exponent, and please use the EXP button next to the answer button usually in your calculator, multiplied by 6.4 exponent 23, multiplied by 1.48 exponent 15, right? and this is divided by, so I'm going to open brackets there, 20.1 exponent 6, 20.1, let's fix that. Okay, exponent 6 plus 3390,000. Okay, and remember this is all squared. Okay, so I'm gonna try and write this in exponential form. I'll just take some details there. Okay, so my answer would be, oh, that's a very huge answer. Okay, I want it in scientific notation. That's 1.15, or you can say 1.2 exponent 14, right? Newtons. So this is the force that the two planets exert on each other. Okay, right, there we go. Now they say to us, we've got 3 statements that are given about the force that Mars exerts on Deimos, right? Mars exerts a greater force on Deimos than Deimos exerts on Mars. That's not true, right? Mars exerts a smaller force. That's not true. Mars exerts the same magnitude of force. Yep, it's definitely equal, right? So they say indicate whether A, B, or C is the correct statement and give a reason for your answer. Definitely it will be C. Why is that? Because of Newton's third law. All right? Newton's third law simply states, right, if body A exerts a force on body B, right, body B will exert an equal but opposite force on body A, right? And that statement is not related to the size of the mass or anything of the sorts. Remember that when two objects exert forces on each other, they will be equal but opposite. Okay, right, so let's go on to the next one. They say to us, we've got a charged ball with a mass of 3 grams that is suspended on a light non-conducting string in a uniform horizontal electric field, right? So the field is 420 newtons per coulomb. The ball is carrying a charge of 6 microcoulombs. The diagram is not drawn to scale. Right, now firstly they say define electric field at a point. Now remember, we say that electric field is the force per unit charge, okay? Or in this case you can say that it is, we say that it is the area in which electrostatic force can be felt per unit charge. Okay, right, so the next one, they say determine the magnitude of the force experienced by the charged ball in the uniform horizontal electric field. Okay, right, so now I want you to please note, in this case we've got the magnitude of the field, we've got the the charge of the ball, right? So we want the force, so we know E is equal to F over Q, right? And, or you can use big Q if you want to, right? So we know that F is equals to Q times E, all right? So this is going to be 6 microcoulombs, 6 times 10 to the minus 6, right? Multiplied by the field is 420, okay? And what do we get there? All right, so let's clear that. 6 exponent negative 6 multiplied by 420, and this will give us a magnitude of, okay, in scientific notation, that gives me 2.5 times 10 minus 3 newtons. Okay, right, so this is going to be our force. And then the next question, they say define weight. Okay, so what is weight? It is a force, right, that the earth exerts on an object, or it is the force of attraction that the earth exerts on an object. I don't know if there's any other better explanation of what weight is. Okay, but there it is right there. Now they say to us, calculate the angle between the light string and the vertical, right? So I want you to please note in this case what's happening there, right? We've got the electrostatic force that is exerted on the sky. Okay, so there it is there. Let's rather do this. I know that there will be force of gravity that's exerted, okay, with the weight, and there will be electrostatic force that causes the sky to move in that direction. Now please, I want you to note, between these we've got the angle theta. We already have found the value of the force, so we can find the weight as well, right? This is equal to m times g, right? And now, because that electrostatic force is opposite and the weight is adjacent, we can use the tan of theta, right? So what I'm going to do is let's find the weight first. That's m times g. That's 3 grams. Now remember, in physics we use kilograms, so we're going to actually divide by 1,000, right? So that's 3 divided by 1,000, which is 0.03. Okay, multiplied by 9.8. Okay, so let's do that quickly. That's 0.003 times 9.8, and we get 0.0294. Okay, newtons, right? So remember what I said, right? We've got the weight here, we've got electrostatic force over there, okay, and we are looking for the angle between the two. So I'm going to use the tan of theta, which will be opposite, which is electrostatic force, divided by the weight. So in this case, my electrostatic force, that's 2.5 times 10 minus 3, divided by, okay, I'm going to use this as is, 0.0294. I don't want to round off just yet. And so, remember, if I'm looking for the angle, I'll say theta is the arctan of that entire expression, right? So I'm going to say shift tan of 2.5 exponent negative 3 divided by 0.0294. Okay, right, so I get an angle of 4.86. So that would definitely be our angle, 4.86 degrees. That's what I get. Okay, right, I hope that makes sense, ladies and gents. All right, so finally, they say the same ball is now given a new charge of negative 12, right, and reaches a new equilibrium. Briefly describe the changes in the angle between the light string and the vertical. Okay, so with a bigger charge, there will be a greater electrostatic force, right? Makes sense, right? Now, if that force is bigger, which means electrostatic force is bigger, the weight remains the same, so definitely this angle would increase. So I would say that angle would increase, okay, right, because there will be an increase in the amount of electrostatic force. All right, I hope that makes sense, ladies and gents. Right, as we swiftly move on to question 8. All right, so we go on to question 8. They say to us the circuit below is a simplified diagram of the setup of a headlamp and starter motor in a car. Right, so they say to us the headlamps are identical. Each headlamp has a constant resistance, okay, of 12 ohms and is rated 55 watts. The starter motor has a resistance of 0.05 ohms. Okay, so let's start there. They say the battery has an unknown EMF and a significant internal resistance. They say define EMF. Remember, EMF, this is the total energy per unit charge within the battery, right? So the total amount of energy per unit charge within the battery. Okay, right. Now they say to us switch S1 is kept open while switch S2 is closed. So S1 is open and S2 is closed. All right. So what will that do? Okay. So in that case, we can see we've got a battery there. Okay, that will definitely mean that some of the current would go there, right? And of course, current would divide and go to the other lamp. Okay, right, there would be a small amount of current, of course, that would go to the starter motor. Okay, remember, current doesn't go through oh no, actually, no. So that means with switch S1 open, right, there would be no current that flows through to the other side. So current would only go in this direction, right? So it would only go to the starter motor. Okay. Right. So let's check. So they say to us the reading on A2 is 10 amperes. Okay. Right, and it makes sense. All the current would go there. Now they say to us, calculate the reading on the voltmeter when switch S1 is open and switch S2 is closed. So we want the reading on the voltmeter, right? So we know 10 amperes of current are passing through. That's 0.05 ohms of resistance. So we know that we're going to say V is equal to I times R. That's 10 multiplied by 0.05. Okay, so which means the voltage there should be 0.5 volts. Right, so voltage should be 0.5 volts. Okay, and then they say to us, okay, so the next question, they say calculate the current through each on. They say switch S1 is now closed and switch S2 is open. So now what's going to happen, we've opened switch S2, right? So there's no longer current that is flowing in there. Okay. And now all of a sudden with this guy closed, all the current would go to your parallel combination. Okay. Right. So in this case, they say to us, calculate the current through each lamp when switch S1 is closed and switch S2 is open. Now, I want us to note, ladies and gents, that So with that setup still being there, right? I know the power rating of each lamp and I know the resistance of each lamp, right? So to calculate the current that would be passing through, I can say, well, power is equal to I squared multiplied by R. My power rating is 55, okay? And in this case, the resistance of each lamp is given as 12 ohms, right? So that's 12. So I can divide both sides by 12 and take the, okay, so I will say 55 divide by 12, okay, and I will take the square root of that because of our answer. Okay, I get 2.14. Okay, so that's 2.14 amperes. Okay, but of course, if they asked you to round that off to one decimal, that would be 2.1. They say determine the reading on A1, right? Now let's look at A1. What would be A1? It would be the total current that is passing through over there, right? So please, I want you to note, ladies and gents, in this case, if I know that each one of them gives me a current of 2.1, right? And 2.1, so it means the current that was passing through A1 would be twice that, isn't it? So which means that the current on A1 will be 2 times 2.1, which is 4.2 amperes. Right, now they say to you, determine the effective resistance of the headlamps connected in parallel. So remember, we say 1 over R parallel. That's 1 over R1 plus 1 over R2. But each one of them had 12 ohms, isn't it? So that would give us 2 over 12. But remember, that's 1 over R parallel. So which means, therefore, R parallel would be equal to 12 over 2, which is 6 ohms, right? Now, please, ladies and gents, if you've got one resistor, you may be able to use, right, RP would be R1 times R2 over R1 plus R2. So that's that's 12 times 12 divided by 12 plus 12. Okay, and this gives us 6 ohms still. Okay, right, now they say to us, write an expression for the EMF of the battery in terms of the current through emitter A1. Okay, so we know that the EMF would be I R plus the internal resistance, right? So if we wanted the value of the EMF, so they said we must write it through as the current in A1. So that would be, that current is 4.2, right, times 6 plus R. Okay, you can continue with this and simplify it further if you want to, right? So in this case, this would be 4.2 times 6. That's 25.5 plus 4.2 R. Okay, so that's 25.2 plus 4.2 R. Okay, so that is the expression. Now they say write an expression for the EMF of the battery in terms of the current through emitter A2. Okay, the resistance of the external circuit and the internal resistance when switch S1 is open and S2 is closed. S1 open and S2 closed. Right. Now remember A2, they said this, we had 10 amperes that were passing through here, right? Okay, so in that case, that would be EMF. Okay, would be I into R plus. Now in that case, our current was 10. Our resistance through the circuit was that 0.05 plus small r. So we said this would be 0.5 plus 10r. Okay, right, so that's how we'd get the expression there. Right, now they say use your expressions in 8.6 and question 8.7 to determine both the EMF and the internal resistance of the battery. Okay, right, now please I want you to note, let's call this equation 1. Okay, so that would be our equation 1 and that would be our equation 2. And what do you note? Both of them are equal, isn't it? So equation 1 is equal to equation 2. So meaning that we've got 25.2 plus 4.2r, right, which is equal to 0.5 plus 10r. Okay, so our battery is complaining. Right, so this would now say to us, we've got 4.2 and 10 over there. If I take my r's, okay, 10 minus 4.2, this would give me 5.8 r. And if I take that value there, 25.2 minus 0.5, okay, I get 24.7. All right, and if I divide both sides by 5.8, my value for R is 24.7, 0.7 divided by 5.8. And I get an internal resistance value of 4.3? Okay. And what about our EMF? All we're going to do is substitute our value for internal resistance into any of the two equations. So I'm going to take equation 2. So that will be 0.5 plus 10 times 4.3. Okay. So I will get 0.5 I will get 43.5 volts. Okay, I hope that makes sense, ladies and gents. Right, so that is what I would get for my values for internal resistance as well as the EMF of the cell. Right, now on to the next question. They say the headlamps are on switch S1. All right, is closed. The starter motor is then switched on. That is switch S2 is also closed, right? So we close both switch S1 and S2. So what happens in this case? They say when both switches are closed, would the brightness of the headlamps increase, right? Stay the same, or will it decrease compared to when only switch S1 is closed? Briefly explain your answer. Now, to quickly go through this, ladies and gents, please I want you to note, the moment we close both switches, now let's go back to our circuit, right? So when I have both switches closed, So both switch S1 and S2 close. So what's going to happen in this case? We're going to have the current, okay? Now, which means I've actually connected a resistor, an additional resistor in parallel, right? Now remember, anytime I connect resistors in parallel, the effective resistance of the circuit decreases, right? So my effective resistance decreases, and so what happens to current? According to Ohm's law, current is, okay, let me just explain there. So adding a resistor in series, okay, a resistor in parallel rather, adding a resistor in parallel will decrease the effective resistance, right? Will decrease the effective resistance, right? So meaning the total resistance of the circuit, or you can say the resistance of the load, right? Now, in this case, what happens? We know that I is equal to V over R. So when I decrease resistance, what happens to current? Current will actually decrease, okay? Now, I want you to please note in this case, the moment I increase the current, right? So remember, what do we want to know? About the brightness of the light bulbs, right? So the moment I increase the current in this case, right? What happens? It means that now my V external, so first of all, it means that my V internal will also increase. Remember, V internal is I multiplied by R internal. So remember that increases, okay? So what happens? It will increase V internal, right? And so what does that ultimately do to the external voltage, right? So now that we've increased the internal voltage, EMF is V external plus V internal. Remember, this guy stays constant, right? But in this case, we've increased the internal voltage, and so that means V external will actually decrease. Now you think about, in this case, what causes brightness? That's going to be V squared divided by R, right? So now that I've decreased the voltage across the batteries, right? What will happen in this case? It means the power, all right, will decrease, and as a result, it means that the brightness will actually decrease. Now, ladies and gents, please find a way, okay, to express that, okay, because it is quite important to know the sequence, right? I said adding a resistor in parallel will decrease the effective resistance, okay, or you can say the total resistance of the circuit, right? If I decrease total resistance, I know current will increase. That will increase V internal, and that will in turn decrease V external, okay? And of course, power is dependent on that external voltage, and so the brightness will decrease, right? Now, they say to us finally, the headlamps are connected in parallel. Why is it important that they are connected in parallel rather than in series? Now, remember, guys, when I connect resistors in series, when one of them burns out, what happens? It means both of them will not be able to work. Why? Because current cannot flow, right? But if I connect them in parallel, right, what am I ensuring? That even if one of them burns out, at least the other one still can function. Okay, right, so that's the advantage of using parallel resistors. And what do you know? Right, we've reached the end of question 10. Right now we're going to start, question 8 rather. Now we're going to start with question 9. Right, now let's go on to question 9. They say to us the headlamps of a bicycle is powered by the spinning wheel of the bicycle, right? They say the wheel turns a magnet inside a coil as it spins. A simplified diagram of the AC generator that powers the headlamp is shown below. Okay, so there it is, that simple mechanic, that simple mechanism there. right? They say state the energy change that takes place, or rather that happens in a generator. Now please remember that a generator converts mechanical energy, movement, okay? So mechanical energy into electrical energy, okay? Please keep that in mind, right? I'm sure every single one of that knows about that in South Africa, given the amount of load shedding, right? Okay, so let's go to the next question. They say, this is an AC generator. Name the component or the component that could be connected inside box X to convert this to a DC generator. Now remember, every time that you want to convert from AC to DC, right, you would have to use a rectifier, right? In this case, we can use a rectifier circuit, okay, or you can say it's a bridge rectifier, okay? All right, bridge rectifier. Okay, right. Remember, that's when you use diodes, right, to try and rectify that circuit, right? The next question says to you, state Faraday's law of electromagnetic induction, right? Please remember it states that the induced EMF is directly proportional. So if you think about it, the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Okay, so we say that the induced EMF is directly proportional, right? This shows us magnetic flux, okay, is directly proportional to the rate of change of magnetic flux linkage. All right, now going on to the next one. They say explain how the spinning magnet generates a current. Okay, now very quickly, right, we know that when the magnet spins, what does it do, right? It's going to change, right, the magnetic flux. So what happens is, as it spins, right, exactly what we explained in terms of Faraday's law, it's going to change the magnetic flux as it spins, right? And of course, this is going to change the EMF, all right, and thus it's going to produce a current. Okay, right, so in this case, as the magnet spins, okay, please, I think I've mentioned that enough. Okay, please make it a point that you write that down. Okay, so the next one says, on the axis given, right, sketch the graph of voltage versus time to show the output of this generator. Show 2 full rotations of the magnet, right? Label this 9.1.5. So what we would have, they said we should show 2 of them. So remember, this is, okay, this is, okay, right. So these are what 2 full rotations would look like. Sorry that my peaks are not equal, but they should be. Okay, so this is what 2 full rotations would look like. Remember, this would be the first one and this would be the second one. Okay, right, and they said we should label this 9.1.5, right? And then on the next question, they say on the same set of axes, right, that is above, draw the graph of voltage versus time for the output of the generator when the wheel turns at half the speed. Now remember, the slower I turn, the lesser the magnitude of the voltage, right? And in this case, they say label this. So the induced voltage should actually decrease, okay, and at half the speed, right? So in this case, my peaks are much less, and also I've got only one full cycle because I'm turning at half the speed. So maybe I should have used a different color, okay, just to show the other one. Okay, and this is 9.1.6, 6. Okay, right now, all right, and the almost last question, they say to us, the headlamp is connected to this generator with a number of diodes as shown below. All right, this is the rectifier circuit we were referring to earlier on. Okay, so they say to us, on the set of axes given, right, this is a rectifier circuit. Okay, they say to us, sketch the graph of the reading on the emitter rather versus time when the wheel is spinning to show the current through the headlamp as the wheel spins. Right, now please, I want you to note, ladies and gents, so now that we put a rectifier circuit, what is it going to do? It's going to convert our AC current into direct current. So I'm expecting to see this. Okay, so what should have been a full cycle there now becomes, remember, it's in one direction this time around. Okay, right, I hope that makes sense. Okay, so the last question, they say a transformer has 11,000 turns on the primary coil, right, and 4,000 turns on the secondary coil, right? So in this case, what they want us to do on the secondary coil, if the output of the transformer is 240 volts. Now remember, on the output, this would be on the secondary coil, isn't it? Okay, so they say, what is the input? So this is very, very simple, right? So our formula just simply says VP, right? That's for primary, over VS, that's secondary. This is simply going to be the number of primary coil turns divided by the number of secondary coil turns, right? And all we are simply going to do, right, so in this case, I am looking for the primary. Remember, I said input, so I'm going to make VP the subject of my formula, but I know my VS is 240, right? NP is, they said primary is 11,000. Oops, that's 11,000 divided by my secondary is 4,000. Okay, right, of course I'm going to make to do some gymnastics there. So this is going to be 11,000 multiplied by 240. Okay, and this is divided by 4,000. Okay, so I get 6. No, actually I said 11. That's 11,000. Okay, times 240 divided by 4,000. Okay, apologies about that. So that will give me, right, so my input should be 660 volts. And of course, this tells me that this is a step-down transformer, right? Because if you look at my primary turns versus my secondary, I've got lesser turns on the secondary coil. And so that is a step-down transformer. All right, and so we come to the end of question 9, and now we are going to get ourselves involved in question 10. All right, let's get ourselves ready for question 10, and that's the last one. It says the work function of certain metals are given in the table below, right? They say light frequency. Okay, we've got our table there. Okay, and they say light frequency of 9 exponent 10, 9 times 10 exponent 14, right, is shown on a sample of these metals in turn, right? They say define work function. Okay, so we know that this is the minimum energy required to emit electrons from a metal surface, right? Okay, so I'm not going to write that down, but of course I know that you will get it, right? Of course. They say determine the energy of a photon of light with a frequency of 9 times 10 to the power 14. Right, so now we're looking for the energy of the photon. And please remember, our magic formula, right? So E is equals to HF, right? So what are we going to do there? We're going to say, right, that's Planck's constant, which is going to be 6.6 times 10 minus 34. Of course, if you are doing the DBE, you're going to use 6.63, right? Okay, multiplied by the frequency in this case is 9 times 10 exponent 14. All right, so let's calculate that. That's 6.6 exponent negative 34, right, multiplied by 9 exponent 14. Okay, so I get that massive value there. Let's do it in scientific. Okay, so that's going to be 5.94 rather, times 10 minus 19 joules. Right, so that would be the energy from the photon, right, of that light. Okay, so 5.94. Now, they say, hence showing any calculation necessary, right, justify which metals will emit electrons when light of this frequency is shone. So what we would need to do, ladies and gents, is let's find out what this energy of the photon is in terms of electron volts. I'm not going to convert all of that in terms of electron volts, but let's rather convert this one, right? So I'm going to say E, that's 5.94 times 10 minus 19 divided by 1.6 times 10 minus 19. Okay, so let's do that. I still have that value there. Okay, and I'm going to say this is divided by 1.6 times 10 minus 19. So exponent negative 19. And I get an answer of 3.71. Okay, right, electron volts. Now, anything that is below this value, right, in terms of work function, right, will be able to emit electrons, but anything that is above 3.71 will not be able to emit electrons. So if I look at that, definitely calcium is below, as well as sodium is below, okay, 3.71. So definitely we'll be able to emit electrons from calcium and sodium, right, because in this case their work functions are lower than the emitted, the energy of the emitted photon. Right, now we look at 10.4. They say to us the intensity of the incident light is halved. Now note they are changing the intensity, right? Okay, explain which metals will emit electrons now. All right, now the moment that we're going to halve the intensity, in this case, remember that intensity does not have anything to do with the energy of the photon, right? So we'll still be able to emit the same ones, but what will be different? Okay, the only thing that will be different is the number of electrons emitted per second. Please remember that, when you change intensity, right, it will not necessarily, well, it will not actually change the kinetic energy of electrons. Okay, right, so in this case it will be the same metals, all right, which were sodium. Okay, so we said it was sodium and calcium. Okay, right, so it would still be the same one, because in this case, as we did say, that changing the intensity will not affect the energy of the photon. All right, now they say to us light with a wavelength of 420 nanometers is shown on a sample of sodium metal, right? Now they say to us, determine the maximum velocity of the electrons for this, electrons that this light ejects. So in this case, we are using sodium, okay? And in this case, we've got a wavelength of 420. So what we can do is we can find out the energy of the photon. That's hc over lambda, right? So in this case, we can say, well, we know E is equal to omega 0, okay, plus Ek. Right, so for sodium, we saw that the electron volts were 2.3, right? So remember, how do I convert it now to joules? You'll say 2.3, which is the number of electron volts, multiplied by 1.6, times 10 minus 19. Okay, the same way that I converted, energy into electron volts, right? So this is plus. Now note, in this case, that's going to be half. Now remember, ladies and gents, when I use the mass here, it's the mass of an electron. So this would be 9.1 times 10 minus 31. Okay, and we say v squared. All right, now let's go on to this side where we're looking at the Planck's constant. Right, so we said this is 6.6 times 10 minus 34 multiplied by the speed of light. That's 3 times 10 to the power 8. Okay, and divided by the wavelength. We're given that as 420 nanometers. That's times 10 minus 9. Okay, so ladies and gents, all we're going to do is do some gymnastics mathematically, right? I'm going to start on the left-hand side and say, well, we've got 6.6 exponent negative 34 multiplied by 3 exponent 8. Okay, and this is divided by 420 exponent minus 9. Okay, so I've got that. I'm going to subtract from it, okay, that entire thing. I'm going to subtract 2.3 times 1.6 exponent minus 19. Okay, all right, and I get that answer. And now we are going to divide, okay? So all of that divided by a half, so 0.5 times 9.1 exponent minus 31. Okay, so I've got that answer there. All right, and now we are going to take the square root of that. So the square root of our answer. Okay, and what do we get? All right, I get a big number there, 4.76. Okay, in fact, 4.77. So V is 4.77 times 10 exponent 5 meters per second. Okay, right, of course you could have looked at it. My calculator can give you that in scientific form, right? So that's 4.77 times 10 exponent 5. Right, and ladies and gents, that is out of 200 marks. I hope that you were able to follow on and enjoy this question paper, right? Otherwise, from me for now, I'll see you guys next time, and please don't forget to subscribe and like, and of course, look out for more content from your favorite uncle. I'll see you guys next time. Sharp, sharp.